ice shelves that have been around the Antarctic Peninsula are breaking up. And what this has done is released the pressure on glaciers. The cork has been pulled, and now the glaciers are free to accelerate and move down into the ocean.
These two big ice shelves that we're concerned about, they're dropping in height about 1 meter a year, and so we're trying to focus attention on these ice shelves.
Well, one of the things that's going on is that there will be a gap in the satellites that have been doing this work for the last 5 or 6 years. ISAT-1 has just about run into its end of life.
The projected launch date for ISAT-2 is 2014 or 2015. Operation Ice Bridge is designed to fill a gap in the data. We're going to fill that gap in by using aircraft platforms, a number of different aircraft platforms, to measure the areas that are of great concern to us.
And it'll provide a baseline data set to compare to future ISAT sensors in space.
The peninsula and West Antarctica down to the Pine Island Thwaites region is warming. The rest of the continent is sort of staying the same. Even though the sea ice overall around Antarctica is either slightly increasing or staying the same, the sea ice in the Amundsen-Bellinghausen sector is retreating. The ocean underneath the sea ice is warming. Not a lot, but it's warming. And the critical ice shelves, the ones we're most worried about from the point of view of sea level rise, are the Pine Island Glacier and Thwaites Glacier. They're losing ice at a rate of about 100 gigatons a year. Sounds like a big number, but it's probably less than 1 millimeter of sea level rise. And so we wanted to get an idea of how thick the sea ice was in this region. And so one thing we're using is the Kansas radar.
The MCORDS radar system is a pulsed radar. We are measuring the thickness of the ice, and we are also measuring the elevation of the bed beneath it, so the scientists can get a sense of how thick is the ice and what's the topography beneath it, and that goes into the models that help them to model the flow and how the ice sheets are going to respond to the forcing functions from the atmosphere. Under the right conditions, we can see if there's liquid water down there or if the bed is frozen onto the ice. So that's useful for modelers as well.
The other tool we have is the device that measures small changes in gravity, the gravimeter. This can measure very small changes, and these are created when the cavity beneath the ice shelves is filled with water. We're able to determine the water depth within that cavity and thereby the topography beneath the ice shelf. And the shape of this topography is going to help determine the stability of these ice sheets.
One of the things that you need to be able to do is to conduct change detection. So that means there's one set of measurements that you've made sometime in the past, last year, 10 years ago, and you like to repeat those lines to see what changes have taken place in that intervening time period.
The ELVIS system, which is the land, vegetation and ice system, it has a similar measurement scheme to the ISAT sensor. The laser measures surface topography, and it also measures surface roughness, and if we're flying over crevasse terrain, then we can measure the depth of the crevasses and the depth of the different reflecting surfaces within the crevasses. And if we come back a year from now or 2 years from now and we measure exactly the same point on the ground, we can tell how much the ground has moved up or down. So we can estimate how much mass has been lost from the ice sheets. And that's an important question right now with global warming and sea level rise.
The Airborne Topographic Mapper is going to be carrying out several objectives. One of the objectives is to fly over flight lines we have done previously. Our instrument is designed to make a very accurate measurement of just the surface of the ice. It does that in a swath underneath the aircraft. The reason we fly a swath is so that we can come back a year later or 5 years later and fly over the same swath and pretty much get 90, 80, 90 to 100% overlap between this year's swath and a swath that was flown sometime in the past. We do 5,000 measurements every second. We'll get many, many tens of thousands of measurements that will fall within 1 meter of a previous measurement. And so by combining the laser data With the radar data, you get a very accurate surface of the ice, you get a very accurate bedrock measurement, you can tell the thickness of the ice.
You know, we've been sort of dreaming about doing these kinds of measurements on a long-range aircraft. Previously, we've used smaller airplanes, and the range, the distance that you can go into Antarctica has been restricted in what you can collect. And the knowledge of what's going on with the climate and the subsequent effects on sea level, they're too important to just let them go not being monitored, not being measured. This airplane brings the long-distance capability to the measurement process so that we can get into more sites of interest in Antarctica and collect a broader range of data that gives you a better look at what's going on in the entire continent.